All right, everyone, here's part 2 of your second review for calculus, the second calculus 2 exam. So let's waste no time, starting with this one here. Assume the following information about the function f. So it tells you f of 6 is 11, derivative of f at x equals 6 is 1/4, and the second derivative is greater than 0 for 6 is less than x less than 6.5. So I think a sketch is the ideal way to interpret this one. Let's start here at 6.5. So we know that this is a concave up function from 6 to 6.5, right? And we know that a concave up function looks something like this, right? Well, since the first derivative is positive, first derivative is 1/4, that means it must be on this half here, where the slope of the tangent line is something positive. Okay. So we got a graph that has concave up shape like this, between 6 and 6.5. So if we wanted to estimate f of 6.5, well, we'd be let's look at the tangent line here at f equals 6. So I sketch the tangent line. Well, now look, since it's concave up, look at the space between these two. Call it delta x. So this is showing that our estimate from the tangent line from the first derivative based on our information should be an underestimate if it's bigger than 11. So the first derivative we know is f prime of 6 is 1/4, right? Well, that would mean that 1/4 would be how much this graph increases if we went one whole step for x. We're going a half of a step for f of x. So here we should say that 11.125 is an underestimate. Because if we go 1/4 based on our approximation in one amount of x, we would go 1/8 or 0.125 in half of that much. So because we have 0.5, I would say best answer is E. So we know that this would be an underestimate. Okay, suppose g prime of 3 is 0, second derivative of g is this function, and g of x are all defined for x within negative infinity, infinity, which is true. Okay, let's go one by one through these statements. First, saying g is local minimum or local maximum. Well, we know g prime of 3 is 0, so it is a critical point. We can do the second derivative test by plugging 3 into the second derivative here. Let's see what that gives us. So 1 minus 3 squared would be negative 2. 3 times negative 2 squared, which would be 3 times 4 is 12. Okay, so that is a positive second derivative, so that means it is concave up here. So if it's concave up and there's a critical point, it looks something like this, right? So that means we'd have a local minimum. Okay, so this one's true. We'd say it is a local minimum. Now let's look at the third statement. G is concave down on the interval negative infinity to 0. Well, all we have to do is just test a value in that interval, plug it into the second derivative. Let's try negative 1. That's in the interval, so let's just plug it in. Negative 1 times 1 minus negative 1 squared. Okay, so that's negative 1 times 2 squared, negative 4. Okay, well, that is a negative second derivative. It means it should be concave down, so I agree with that. It's concave down on this negative infinity to 0 interval. All right, now the last one is saying it changes concavity at 0 and 1. Well, let's plug in. We know for values less than 0, we are concave down, right? So now let's plug in a value greater than 0. Let's try between 0 and 1. Maybe g prime prime of 1/2. Well, this would be 1/2. 1 minus 1/2 squared. Well, that would be positive number times positive number. So before 0, it's concave down. After 0, it is concave up. So it changes concavity to x equals 0. This one's good. So, okay, it's concave up between 0 and 1. Now let's try one after 1. So maybe g prime prime of 2. 2, 1 minus 2 squared. This is, again, since this is squared, this would be 2 negative 1 squared, which is 2. So it's positive still, so it doesn't actually change concavity at x equals 1. Even though if you plug 1 into this formula, you get 0. So the concavity doesn't actually change at x equals 1. So I'd say 2 and 3 are your correct answers.
So let's look at this next problem. It says find the critical points of f of x equals 2x to the fourth power minus 5x cubed plus 3 and classify them as corresponding to local maxima, local minima, or neither, and justify your classification of the critical points without referring to a calculator-generated graph. So let's write down the function f of x equals 2x to the fourth power minus 5x cubed plus 3. And in order to find the critical points, right, that's my first step, I want to find the critical points. I need to set the derivative equal to 0, right? Critical points are places where the derivative is 0 or the derivative does not exist. So I need to first use my standard differentiation rules to find the derivative. And here I would use the power rule, right? So I get 8x cubed minus 15x squared. And now I want to set this guy equal to 0 to solve for places where the derivative is 0. Okay, I see that both of these terms, 8x cubed and negative 15x squared, both have a factor of x squared in common. So I'm going to pull out that x squared in both of those. Okay, and so now I can use my zero product property to say that either 0 is equal to x squared or 0 is equal to 8x minus 15. Okay, and so for the first guy, 0 is equal to x squared. I take the square root of both sides, so plus or minus the square root of 0 is equal to x, or simply x is equal to 0. And for the latter, I move over that 15, right? I add 15 to both sides, and then I divide by 8, so I get x is equal to 15 divided by 8. So there are my two critical points. X is equal to 0, and x is equal to 15 divided by 8. And now I want to classify them corresponding to local maxima, local minima, or neither, and I'm going to do this using the first derivative test. So first derivative test. Okay, so I'm going to draw a number line, and here is x equals 0, and here is x equals 15 over 8. And I want to analyze the intervals around those particular spots. So for example, from negative infinity to 0, from 0 to 15 over 8, and from 15 over 8 to infinity. And so I'm going to choose a value and plug it into the derivative, and that's going to tell me at those spots, at every value in those intervals, if I plug them to the derivative, I would either get a positive or a negative output. And that's going to tell me what the function is going to look like. So for example, let's look at this particular interval from 0 to 15 divided by 8. And a good testing point is probably x equals 1. 1 lies in that interval. Okay, so I'm going to plug in x equals 1 into the derivative, so f prime of 1. And I get 8 times 1 cubed minus 15 times 1 squared. Okay, and that gives me negative 7. Okay, so that tells me that all the values in this particular interval are negative. So I'm going to draw a negative sign. And that tells me that the function is going down. Okay, so I'm going to do the same for the next interval, negative infinity to 0. So let's choose a good testing point. So a good testing point is x equals negative 1. I'm going to plug in negative 1 into the derivative. And if I plug that into the derivative, I get 8 times negative 1 cubed minus 15 times negative 1 squared, and I get negative 23. Okay, so that tells me that all values, if I plug them into the derivative, they're negative, and so my function is going down. And lastly, let's do the last interval. So a good testing point between 15 divided by 8 to infinity would be x equals 2. So I'm going to plug in x equals 2 into the derivative. Okay, so 8 times 2 cubed minus 15 times 2 squared, and you get 4. So all the values in that interval, if I plug them into the derivative, they are positive. And that tells me my function is going up. Okay, and now I can see that at x equals 15 divided by 8, to the left it's going down, and then to the right it goes up. So we have a local minima at this particular spot. And for the other critical point, it goes down to the left at x equals 0 and down to the right at x equals 0. So we have neither. Okay, so let's write all of this in words. So at x equals 15 over 8, f of 15 over 8 is a local minima. Remember, our x values are associated with critical points, and our outputs are local minima or local maxima. And then at x equals 0, f of 0 is neither a local minima or local maxima. And our justification was using the first derivative test.